Good morning, class. We are starting today on doubling time and halving times, and that is Unit 8B, doubling and half time. If you look at this little demonstration, you see a little, I don't know what it is, like a little amoeba, a little cell there. And on day 0, we have 1, and then day 1, we have 2, and then on day 2, we have 4, on day 3, we have 8 there. And you'll notice that each day, we end up with the double amount of amoebas that we had the day before. What we would call that is doubling time of one day. Every day, the population doubles. And that's what we're going to be studying, as well as halving times, which we'll talk about here in a second. Exponential growth happens. Remember that things really grow quickly in exponential growth. They just take off. And if that happens or that occurs, and we have something called doublings, repeated doublings, and then if something is decaying, like radioactive material decays, and if it decays exponentially, then we would have repeated halvings of the material. However, in most cases of exponential growth or decay, we are given a rate. So it'll say it's a 7% growth rate or a 10% decay rate. It's a percentage that we're given. We're not given the time that is required for the doubling or having to occur. So sometimes we'll be converting between growth or decay rates and then doubling or halving times. And that's what this lesson is about. If we have doubling time, that refers to how much time is required for each doubling in exponential growth to occur. If we have halving time, that's the time required for each halving in exponential decay. If you remember the magic leprechaun example, the doubling time for the magic penny was 1 day because the pennies doubled every night. When she went to bed, she woke up again, and the next morning she had double the amount of pennies. So that was 1 day for the doubling time. And then if we want to, we can find the rate and everything else that we need to from that information. So we'll be going back and forth a little bit. These are just some examples that you see down here. In 10 years or 1 doubling time, the population, if it started with an initial population of 10,000, and the doubling time is 10 years, the new population after the 10 years had passed will double to 2 times 10,000 or 20,000. If 20 years pass, that means 2 sets of doubling time, and that would be 4 times 10,000 for 40,000, because it would double twice, which is 2 to the second power. So we're taking 2 because 2 is a doubling factor. We take 2 to the second power when 2 doublings have occurred, 2 to the first power when 1 doubling had occurred, and the time had passed for that. If we have 30 years, that's 3 doubling periods, so 3, and with 3 doubling periods, that would be 2 to the third, or 8 would be our factor or multiplier, and we'd have 8 times 10,000 in our population after 3 doubling times had passed. All right, so pretty easy. We have a formula that we will use, and you'll use it quite prevalently on your homework. After a time t, an exponentially growing quantity with a doubling time, notice this little symbol here, t with a little double below it. That means we say doubling time when you see that. It increases in size by a factor of 2 because 2 to a power is our doubling quantifier. T time, that's just time, how much time has passed divided by the doubling time. And if you do that, then you're going to come up with the factor of growth there that we're going to use. All right, so doubling time would be how much time needs to occur for that doubling to occur. And when we place it in this little factor here, this 2 to the t over double time, then we have a new value of growth quantity. And that factor that is a multiplier, we multiply it by the initial value. And then we have how much we would have after a specific amount of time. And it's pretty exciting, pretty cool. So compound interest formula. Compound interest in Unit 4B, remember we studied all of the interest rates and everything in Unit 4. It produces exponential growth, which is awesome because it's money. And exponential growth occurs because of an interest-bearing account growing by the same percentage every single year. So every year, a percentage of growth occurs. And if that's the case, then you're going to have a doubling time at some point. So suppose, if you want to figure that out, you could do that. And suppose your bank account already did that for you, or your bankers already did that for you. And there's a doubling time of 21 years, they tell you. By what factor does your balance increase in 50 years? So what you're going to be figuring out is a multiplier that will tell you how much your money has grown after 50 years if the money does double in the account after 21 years. I'm going to actually go to my ImageMate here. We're going to just do the problem here because I can't write on my screen at work. So compound interest, here we go, has a doubling time of 21 years. So that's your T double is 21 years. And then by what factor does your balance increase in 50 years? So that's our little t. Our little time is 50 years. All right, so by what factor means you're just going to take part of our equation, this part right here, 2 to the time divided by the doubling time. And we're going to do that in our calculator. Let's see if it's showing today. It is. How sweet. 2 to the 50 divided by 21. Make sure that's in the exponent position. 5.2. 5.21. So that's our multiplier. For instance, if at the beginning, if you have an initial amount of $1,000 that you placed into your account, and you multiply that by 5.21, then after the 50 years, you would have $5,210 in that account. See, it's a multiplier by your initial amount, and that kind of gives you our formula that we talked about before. Our initial value is 1,000. 2 to the time divided by double time is 5.21, and you multiply that and come up with the amount in the balance after the 21 years. It's all related, all great. Math is awesome. All right, we're going to do the next example here. This is something like you might get in your homework. What is doubling time? Suppose a population has a doubling time of 14 years. By what factor will it grow in 42 years? So doubling time, of course, is the time required for each doubling in exponential growth to occur. So I'm going to just write that. Doubling time is the time required for each doubling in exponential growth. Okay, we asked that on homework. By what factor will it grow in 42 years if T double is 14 years? That means little t would be 42 years. So in order to come up with that factor, you know that's the part of the equation, t over double time part. That's your factor of growth. So we'll have 2 to the little t is 42, and big T double time is 14. So if we place that in the calculator, I think 14 goes into 42 3 times, but I could be wrong. 2 to the 42 divided by 14 is, 3. So 2 to the third power, or 8. So that is our factor in this case, in this specific case. All right. Okay, so that's how you do doubling time, and that's your formula. Most importantly, of course, are going to be those, the 2 parts to the formula, which you have your new value. Generally, it's a new population, and it's equal to your initial value times 2 to the t over double time. Remember, this is going to be your factor of growth, too, that part. All right, let's go back to the slides, and we'll do the next section. I didn't actually put this in your notes, but I just wanted to show you the first, second, and third doubling in this little population, Power Town. Remember Power Town from, I don't know, I think it was last lesson. But you'll notice that we went from 10,000 to 20,000, so our population doubled in 14 years. That's our first doubling. And if we go from there another 14 years to 28 years, our second doubling occurs. So that's 2 to the second power, or 40,000 is our population, because we would multiply, remember, our initial population, 10,000, by 2 to the second power. And then here we have another 14 years has passed, so a third doubling would happen, which is 2 to the third power. And there you have 8 times your initial population of 80,000. So pretty cool. All right, approximate double time formula. So now we have a new formula, which is a great formula. It's a formula for growing exponentially at a rate of p% time per time period. The doubling is approximately 70 divided by p. And that's given the percent. We don't change it to a rate at all. We just place that actual percent into the formula. So if we want to find an approximate doubling time, we can take 70 and divide it by a percent, given the percent. Of course, we'll have to be given that in our problems that we're given. But this approximation is not great. It has its limitations, but it is perfect for any growth rates that are under 15%. Anytime the growth rate exceeds 15%, it's not the best approximation. It just breaks down. Okay, so we'll use those in your homework a little bit, and that's in your formulas there. All right, doubling time of a bank account balance is 12 years. By what factor does it grow in 48 years, in 96 years? So we're going to try these two examples now. It says by what factor. So when you see that by what factor, remember that's 2 to the t over double time. All right, that's going to be just the part of the formula for that. These don't have the approximation, do they? But that's all right. So 48 years and 96 years. This is just the type of problem you might get in your homework. So if your doubling time is 12 years, so t double is 12 years. Then first we need to figure out for 48, that will be little t, 48 years, and little t is 96 years. So with that, we're going to take our factor part, 2 to the time, which is 48 over 12 double time, and then 2 to the 96 over 12. And that I just did them both at the same time, but 48 divided by 12 is 4, so 2 to the 4th or 16. In the homework with the double time, generally they leave it in the power formula, 2 to the 4th. As an answer, you would just type in 2 to the 4th, not 16. And then this is 2 to the 8th. And that's for obvious reasons. You would leave 2 to the 8th. It's quite a large number, so I'll just type in 2 to the 8th to make things a bit simpler. All right, next example. The initial population of a town is 3,900 and it grows with a doubling time of 10 years. What will the population be in 14 years? So this time you're given an initial population, so we're going to be using the entire formula, wherever that was. It's right here. Initial value times 2 to the little t over big double time. All right, so we're going to take 3,900, which is the initial population. We're going to multiply it by 2 to little t. Now, little t is 14 years. That's how much time is passing when we're figuring out what the new population will be. And then over double time, which is 10 years. All right, and with that, you can just place that right in the calculator. So 3,900 times 2 to, I guess it would help if you saw as I was putting it in. 2 to the 14 divided by 10. Divided by 10. And that is 10,292. So we'll just round to the nearest person or whatever thing in the population. And that is your new population. 10,292. All right. Okay, so I'm going to actually pause this because the videos don't load after 13 minutes. So just stop now, and then you can go to the second video, and we'll start the second video.